Dam break modeling is a very important engineering task. It involves simulating what happens when a dam fails. This process helps us understand the potential floodwaters. We look at how fast the water will travel downstream. We also determine how deep and wide the flooding could be. This information is crucial for protecting people and property. Knowing the risks allows communities to prepare for such an event. The primary goal is always to enhance safety and reduce potential harm from a dam failure, which can be catastrophic if not properly anticipated and prepared for by all stakeholders involved. The consequences of a dam failure can be truly devastating. History has shown us many examples of such unfortunate events. A sudden release of a large volume of water causes extreme flooding. This can lead to significant loss of human life. It can also destroy homes, businesses, and critical infrastructure like roads and bridges. Beyond the immediate physical destruction, there are also long-term environmental impacts. Ecosystems can be severely damaged by the force of the water and the sediment it carries. Understanding these severe potential outcomes underscores the vital necessity of thorough dam break analysis and careful planning. Dam break modeling plays a critical role in developing emergency action plans, often called EAPs. These plans are essential for any dam. An EAP outlines procedures to detect, evaluate, and respond to emergency conditions at a dam. A key component of an EAP is the inundation map. These maps are produced from dam break models. They show the areas that would be flooded if a dam were to fail. This helps emergency managers make informed decisions. For instance, they can identify evacuation routes and shelter locations based on these detailed flood predictions, ensuring a more coordinated and effective response. The insights gained from dam break modeling are vital for many different groups. Dam owners use this information to understand their liabilities and responsibilities. They can also use it to prioritize dam safety improvements. Regulators rely on these models to ensure dams meet safety standards. Communities downstream depend on accurate modeling for their safety and preparedness efforts. By understanding the potential flood, proactive measures can be taken. These measures include public awareness campaigns, zoning regulations, and infrastructure hardening. It is a collaborative effort to mitigate the risks associated with these important structures, ensuring long-term resilience for everyone. HEC-RAS is a widely recognized software for hydraulic modeling. The name stands for Hydrologic Engineering Center's River Analysis System. It was developed by the U.S. Army Corps of Engineers. This software is used by engineers all over the world. It can model water flow in rivers and channels. One of its most important capabilities is simulating unsteady flow conditions. This makes it particularly well suited for analyzing dam break scenarios. Its robust features and continuous development make it a standard tool in the field of water resources engineering, providing reliable results for complex hydraulic situations. HEC-RAS has specific features designed for dam break analysis. It allows engineers to simulate the breaching of a dam. The software can model how the breach forms and grows over time. It then calculates how the flood wave moves downstream. This includes predicting water surface elevations, flow velocities, and arrival times at different locations. Users can input detailed topographic data for the river valley. They can also specify the characteristics of the dam and the potential breach. This level of detail allows for a comprehensive simulation of the entire dam failure event, from initiation to downstream impact. The process within HEC-RAS involves several key steps for dam break modeling. First, the geometry of the river system and the dam itself is defined. This includes cross-sections of the river and the structure of the dam. Then flow data such as the reservoir level is entered. The crucial part is defining the breach parameters. These parameters tell HEC-RAS how the dam is expected to fail. Once all data is input, HEC-RAS solves complex hydraulic equations. It computes the outflow hydrograph from the breach and routes this flood wave through the downstream valley, providing detailed output for analysis. There are many advantages to using HEC-RAS for dam break studies. It is considered an industry standard, and its results are widely accepted by regulatory agencies. The software is very comprehensive, offering one-dimensional and two-dimensional flow modeling capabilities. This allows for accurate representation of complex floodplains. HEC-RAS is also well supported with extensive documentation and training materials. The Hydrologic Engineering Center continually updates the software. This ensures it incorporates the latest research and computational methods, keeping it at the forefront of hydraulic modeling technology for engineers and planners. When we model a dam break in HEC-RAS, certain breach parameters are absolutely essential. These parameters describe how the dam will physically fail. They are the core inputs that control the simulated flood. Getting these parameters right is crucial for an accurate model. If the breach parameters are incorrect, the resulting flood predictions will also be incorrect. This can lead to poor decisions regarding emergency preparedness and public safety. Therefore, careful consideration and selection of these parameters form the foundation of any reliable dam break analysis, directly influencing the trustworthiness of the study's conclusions. The key breach parameters can be grouped into three main categories. The first category is related to breach formation. This describes how the breach starts and what triggers it. The second category concerns the breach dimensions. This includes the final width and depth of the opening in the dam. The third category is the breach development time. This refers to how long it takes for the breach to form fully, from initiation to its final size. Each of these parameters plays a distinct role in shaping the characteristics of the flood wave released from the failing dam. Understanding them individually is the first step. These breach parameters are not entirely independent of each other. They are often interrelated. For example, the material a dam is made of will influence both the likely dimensions of the breach and how quickly it forms. A dam made of easily erodible material might develop a wide breach relatively quickly. Conversely, a more resistant structure might result in a slower, narrower breach. This interdependence means that engineers must consider the parameters holistically. They should ensure the chosen values are consistent with the type of dam and the anticipated failure mechanism, creating a coherent picture of the event. The results of a dam break model are highly sensitive to the chosen breach parameters. Small changes in these input values can lead to significant differences in the predicted peak flow, flood extent, and arrival times. For instance, a faster breach development time will typically result in a higher peak outflow. A wider breach will also release more water more quickly. Because of this sensitivity, engineers often perform sensitivity analyses. This involves running the model with different sets of parameters. This helps to understand the range of possible outcomes and identify the most critical assumptions in the modeling process. Breach formation refers to the very beginning of the dam failure process. It describes how the opening in the dam starts to develop. There are several ways a dam can begin to fail. For earthen dams, common failure mechanisms include overtopping and internal erosion, also known as piping. Overtopping occurs when the water level in the reservoir rises above the crest of the dam. Piping is when water seeps through the dam, creating a small tunnel that gradually enlarges. For concrete dams, failures might involve structural issues like cracking, sliding, or overturning of a monolith section, often related to foundation weaknesses or extreme loads. In the case of earthen dams, piping is a frequent cause of failure. This process often starts with a small amount of seepage. If the seepage carries soil particles, it can gradually create a small pipe or conduit through the dam embankment. As this pipe enlarges, the flow of water increases, leading to more erosion. Eventually, the roof of the pipe can collapse, leading to a rapid and often catastrophic breach. The location where piping initiates is important. It could be near a conduit, at the abutment, or within the main body of the embankment, influenced by soil properties and construction quality. For concrete dams, the initiation of a breach is different. These structures are much more rigid than earthen dams. Failure might begin with the instability of one or more monoliths, which are the vertical sections of a gravity dam. This could be due to excessive water pressure, earthquake forces, or deterioration of the concrete or foundation. Foundation problems, such as excessive uplift pressures or erosion of the foundation material, can also lead to failure. Unlike earthen dams, the initial breach in a concrete dam might occur suddenly, involving a large section of the structure rather than a gradual erosion process. HEC-RAS allows engineers to specify details about breach initiation. For example, the modeler can set the initial elevation where the breach begins. For an overtopping failure, this would typically be at the lowest point of the dam crest. For a piping failure, the user can specify the starting elevation of the pipe. The software then uses this information along with other breach parameters to simulate how the opening grows over time. Understanding the likely mode of failure, whether it's overtopping, piping, or structural collapse, is the first critical step in defining these initial conditions for the HEC-RAS model, guiding subsequent parameter selection. Section 5. Breach dimensions, sizing up the opening. Breach dimensions define the final size and shape of the opening in the dam after it has failed. These are critical parameters in HEC-RAS. The primary dimensions include the final average breach width and the final breach depth. Another important aspect is the slope of the sides of the breach. These dimensions collectively determine the maximum area through which water can flow out of the reservoir. Accurately estimating these dimensions is vital because they directly control the peak discharge of the flood wave. A larger opening will generally result in a higher peak flow and a more rapidly draining reservoir. Several factors influence the final breach width. The type of dam material is a major factor. Earthen dams made of erodible soils tend to form wider breaches compared to those with more cohesive or rocky materials. The height of the dam and the volume of water stored in the reservoir also play significant roles. Larger reservoirs and taller dams can exert more erosive force, potentially leading to wider breaches. Empirical equations, which are based on historical dam failure data, are often used to estimate the likely breach width. These equations typically relate breach width to factors like dam height and reservoir volume. The final breach depth is another crucial dimension. For most earthen dams, the breach is often assumed to erode down to the original streambed or a non-erodible layer within the dam's foundation. This means the breach depth is effectively the height of the water behind the dam, or the height of the erodible material. In some cases, there might be a hard rock foundation that limits how deep the breach can become. For concrete dams, the breach depth might be determined by the height of the failed monolith or section. Careful site investigation can help identify potential limits to vertical erosion. The side slopes of the breach describe how steep the sides of the opening are. This is usually expressed as a ratio, such as 1 vertical unit to x horizontal units, 1 vxh. For earthen dams, the side slopes depend on the stability of the soil material forming the sides of the breach. Cohesive soils might stand on steeper slopes, while sandy soils will form flatter slopes. Typical values for earthen dam breach side slopes range from nearly vertical, 0h1v for very cohesive soils or short development times, to 1 vertical unit to 1 or 2 horizontal units, 1v1h or 1v2h, for less cohesive materials. HEC-RAS uses these dimensions to calculate the geometry of the flow area as the breach develops. Section 6. Breach development time, the pace of catastrophe. Breach development time, often denoted as TEF, is a critical parameter in dam break modeling. It represents the duration it takes for the breach to grow from its initial formation to its full, final dimensions. This time frame is incredibly important because it significantly influences the characteristics of the resulting flood wave. A very rapid breach development will lead to a sudden release of a large volume of water. This creates a flood wave with a high peak discharge and a steep rising limb on the hydrograph. Conversely, a slower breach development allows the water to be released more gradually over a longer period. The breach development time directly impacts the peak outflow from the dam and the warning time available for downstream communities. If a breach forms very quickly, the peak flood will be higher, and it will arrive downstream sooner. This reduces the time available for evacuation and emergency response. If the breach develops more slowly, the peak flow will generally be lower, and its arrival will be delayed. This can provide more valuable time for people to move to safety. Therefore, an accurate estimation of TEF is essential for effective emergency planning and for assessing the true hazard posed by a potential dam failure. Many factors influence the breach development time. The type of dam is a primary consideration. Earthen dams, especially those made of easily erodible materials, can fail relatively quickly, sometimes within a few hours or even less. The height of the dam also matters. Taller dams with more water pressure may erode faster. The mechanism of failure is also important. For instance, an overtopping failure that rapidly erodes the downstream face might progress faster than some piping failures. For concrete dams, the development time might represent the time it takes for a section to topple or slide, which could be very short once instability occurs. Estimating TEF can be challenging. Engineers often rely on empirical equations derived from historical dam failures. These equations typically relate TEF to factors like dam height, dam material, and sometimes the volume of water. For example, some guidance suggests that breach formation times for earthen dams can range from about 1/10 of an hour to several hours. For concrete gravity dams, the failure of a monolith could be almost instantaneous once it starts. Given the uncertainty, it is often wise to conduct sensitivity analyses in HEC-RAS, testing a range of plausible breach development times to understand their impact on the flood predictions. Section 7. Estimating breach parameters. Methods and guidance in HEC-RAS. Estimating breach parameters accurately is one of the most challenging aspects of dam break modeling. There is inherent uncertainty because every dam and every potential failure scenario is unique. We cannot perfectly predict how a specific dam will fail. However, engineers have developed several methods and sources of guidance to make reasonable and defensible estimates for these critical inputs in HEC-RAS. These methods often combine empirical data from past events with engineering judgment. The goal is to select parameters that represent a plausible failure scenario for the specific dam being analyzed, acknowledging the inherent uncertainties involved. Empirical equations are widely used for estimating breach parameters, especially for earthen dams. These equations are derived from statistical analysis of data collected from historical dam failures. Well-known sets of equations include those developed by Froelich, McDonald and Langridge-Monopolis, von Thun and Gillette, and Xu and Zhang. These equations typically predict breach width, side slopes and development time based on inputs like dam height, reservoir volume and sometimes dam type. HEC-RAS itself incorporates some of these predictive equations directly within its interface, allowing users to calculate initial estimates for breach parameters based on dam characteristics. While empirical equations are useful, they have limitations. They are based on a finite data set of past failures, and the specific dam being studied may have characteristics different from those in the dataset. Physical erosion models offer a more detailed approach by attempting to simulate the actual erosion processes during breach formation. These models can be more complex and require more detailed data about soil properties and hydraulics. However, they can provide valuable insights, especially for unusual dam types or conditions. For most practical applications, empirical methods combined with sound engineering judgment remain the primary approach due to their relative simplicity and accessibility. Ultimately, estimating breach parameters often involves an iterative process. Engineers typically start with empirical equations or published guidance. They then consider site-specific conditions such as the dam's construction materials, foundation conditions, and known vulnerabilities. Expert judgment based on experience with similar dams or failure modes plays a crucial role. It is also highly recommended to perform a sensitivity analysis. This means running the HEC-RAS model with a range of different breach parameter values, like low, medium, high estimates, to see how these changes affect the downstream flood predictions. This helps to bracket the potential outcomes and understand the model's sensitivity. Section 8. Breach scenarios and their impact on flood waves. When performing a dam break analysis, it is often necessary to consider multiple breach scenarios. This is because a dam might fail in different ways, or under different conditions. For example, an earthen dam could fail due to piping, which is internal erosion, or due to overtopping during a large flood event. These different failure modes can lead to different breach characteristics and, consequently, different flood waves. By analyzing various plausible scenarios, engineers can get a more complete understanding of the potential risks. This allows for more robust emergency planning that covers a wider range of possibilities. A common distinction is made between a sunny day failure and a flood failure. A sunny day failure typically refers to a failure that occurs under normal operating conditions, often due to an internal flaw like piping. In this scenario, the reservoir might be at a normal level, and the downstream river flows might be low. In contrast, a flood failure, such as an overtopping failure, occurs during extreme hydrologic conditions. The reservoir is already very full, and the downstream river is likely already experiencing high flows. These different initial conditions will significantly affect the nature and impact of the dam break flood wave. The specific breach parameters chosen for each scenario will greatly influence the resulting flood hydrograph. For instance, a scenario with a rapid breach development time and a large final breach width will produce a flood wave with a very high peak discharge and a short duration. This type of flood wave can be extremely destructive due to its power and suddenness. Conversely, a scenario with a slower breach development and a smaller breach width will result in a flood wave with a lower peak discharge that is spread out over a longer time. This might lead to more prolonged flooding, but with less intense destructive force at any given moment. The differences in flood waves generated by various breach scenarios have direct implications for downstream inundation. A higher peak flow will generally lead to deeper and more extensive flooding, The timing of the flood wave is also critical. Faster developing breaches result in less warning time for downstream communities. HECRAS modeling allows engineers to quantify these differences. By comparing the inundation maps and flood arrival times for different scenarios, emergency managers can better understand the range of potential impacts. This helps in developing more comprehensive and adaptable emergency action plans that can address various contingencies effectively. Section 9. The importance of accurate parameters for safety and preparedness. In conclusion, the selection of appropriate breach parameters is a cornerstone of reliable dam break modeling in HECRAS. These parameters, breach formation, dimensions and development time, dictate the simulated outflow hydrograph from a failing dam. As we have discussed, even small variations in these parameters can lead to substantial differences in the predicted flood characteristics. Therefore, engineers must dedicate careful effort and sound judgment to their estimation. The accuracy of these parameters directly translates into the reliability of the entire dam break study, which underpins crucial safety decisions. Accurate breach parameters lead to more dependable flood inundation maps and risk assessments. These maps are vital tools for community planning and for understanding who and what is at risk. If the breach is modeled as too small or too slow to form, the predicted flood extent might be underestimated. This could leave vulnerable populations unaware of the true danger. Conversely, overly conservative parameters might exaggerate the flood, leading to unnecessary alarm or resource allocation. The goal is to achieve a realistic representation of a plausible failure event, allowing for informed risk management and mitigation strategies based on solid technical analysis. The outputs from HECRAS dam break models driven by these breach parameters are fundamental to developing effective emergency action plans, or EAPs. EAPs outline procedures for warning, evacuation, and emergency response. The predicted flood arrival times, water depths, and inundation areas inform evacuation routes, shelter locations, and the timing of warnings. If the breach development time is underestimated, the available warning time in the EAP might be insufficient. Therefore, the integrity of the EAP and its ability to save lives and protect property hinges significantly on the quality of the underlying dam break modeling and parameter selection. Ensuring safety and preparedness in the event of a dam failure is a continuous responsibility. The field of dam break modeling is always evolving with new research and improved understanding of dam failure mechanisms. It is important for engineers to stay updated with the latest guidance and tools like HECRAS. By diligently applying best practices in selecting breach parameters, conducting sensitivity analyses, and clearly communicating the uncertainties, the engineering community can provide the crucial information needed by dam owners, regulators, and emergency managers. This collaborative effort ultimately enhances public safety and builds more resilient communities in the shadow of these vital, yet potentially hazardous